All right, so I'm going to talk a little bit about the basic concepts of NeuPSL and a little bit of how it works. So, as Shamil already said, neuroprobabilistics of logic is based on probabilistics of logic that we have already seen with Professor Simari. Here we have an example of a possible rule for a PCL program that basically saying that if image 1 is from species, and then if image 1 is the same entity than image 2, then image 2 is probably of the same species than image 1. It's also from species, right? So in this type of programs, we have that atoms are instantiated with both observed data and neural predictions. So in this case, this neural predicate, the convention is that when the predicate is called neural, it means that the value of this predicate is assigned by a neural network. For example, the authors said that this same entity could have its value taken from some part of the data. For example, they say that image 1 may have a similar caption than image 2, or that image 1 may be from the same, the image has been taken from the same device and in a short period of time. So based on that data that we already have on our database, we could calculate a score for this same entity. And note also that we have this class predicate that is saying almost the same thing that this neural predicate, but the difference is that this class predicate is inferred from this rule, while this neural predicate gets its value directly from a neural network. And each rule, as in PSL, each rule is assigned to a weight, and the weight quantifies its relative importance in the model. And this weight is also calculated using a neural network. This is like the symbolic part of the neural calculation, while this value of neural is like the the neural part of the predicates calculation. And rules can be hard or soft constraints. If they don't have a weight associated to them, they are considered hard constraints. It's equivalent to say that they have a weight of 1. And basically, you cannot have a case where you have where you can derive a rule that there is a hard constraint and you don't do it. And the last thing is that this PSL have an open world assumption. All PSL programs can have an open world assumption or a closed world assumption. If they have a closed world assumption, then they consider that each constant that they haven't already seen, then any predicate evaluating that constant will have a value of 0. That is, there is a closed world assumption. But if there is an open world assumption, you can have predicates that are instantiated with constant that we haven't already seen, right? Mostly because we have neural networks that can calculate those values, or we can have possibly information that allow us to calculate the value for predicates with constant that we haven't already seen. Then the process of grounding is basically when you have when you instantiate all variables inside an atom with real observed data, both with observed data and neural predictions, basically because you'll need neural networks to calculate the values of the predicates. And when atoms are instantiated with elements from data, they're called ground atoms, and valid combination of ground atoms create ground rules. So just notice that we have one rule, and when we ground that rule, again, taking the example in the paper, let's say you have 2 images and 3 classes. We have image 1, ID1, and ID1 and ID2, and let's say you have cats, dogs, and frogs. Then in that case, we would have 6 rules, right? So we have to instantiate every rule with all possible combinations of observed data. So potentials are basically, in a very short way of saying it, is the calculation of the loss function per each grounding rule. So when each grounding rule creates 1 or more potentials, depending on the grounding, basically, they define a value over x, y, and CNN, right? So X, for example, in this case, could be the images, the IDs of the images. Y could be the labels I want to assign to the images, cat, dog, or frogs, in the example previously mentioned. And this CNN would be the neural networks considered as a function that assign a value to certain predicates. So all logical rules are relaxed using Lukaszewicz continuous value logical semantics. So there is a way of calculating a real value per each rule. And each potential phi sub I is associated with the parameter that is WPSL sub I that is inherited from its instantiating rule. So basically, there is one row in the symbolic neural parameters that is associated with each grounded rule. And potentials and weights from the instantiation process are used to define a deep hinge loss Markov random field. I'm going to talk a little bit more about that in the next slides. So first, before defining the Markov random field, well, we're going to define the deep hinge loss potential. So deep hinge loss potential is basically a calculation of a loss function for a specific y, x, and CNN. So sorry, and CNN with a x. Well, same that Shannon said before. It's a neural function with the parameters of x and the parameters of the learning process of the neural network assigned. And this it's the maximum between that loss function and 0. And they also have this alpha variable that can be 1 or 2, depending if you want to have a loss function that is linear or a quadratic. So basically, the idea is that it's the loss function applied to one grounded rule, and then using this deep hinge loss potential, you can define deep hinge loss energy function. And the idea of this deep hinge loss energy function is that you have to divide all rules in all different possible partitions. So this shape inside T1 is for each possible partition that you can create combining rules. You have the capital phi sub I that is going to be the summation of all the deep hinge loss potentials of all the rules inside that partition. And then then we define the bold capital phi that is it's a vector containing all capital phi sub I for all possible partitions of the grounded rules. Once we have this bold capital phi, we define the energy function basically as a summation of each capital phi sub I multiplied by the corresponding row on the matrix of symbolic parameters. Sorry, and which is basically the same thing as multiplying the matrix of symbolic parameters transposed by the bold capital phi. And then using this, we define a deep hinge loss Markov random field with random variables and condition on x and n as a probability density of, well, this form. I'm going to explain this formula. So basically, we have this normalization constant in the same way that we had them when we had PCL program. And then this normalization constant is applied to the exponential of the negative energy function. And one thing that I think it's important to note is that this function is partitioned depending if the x and y belong to this omega set. The omega set is basically all the possible combinations of x and y that are valid. So when you constrain the program to all x and y that are valid, you have like a finite set. There can be very big, but it's a finite set. And the probabilistic is going to be, well, this calculated value if the combination of x and y is valid and 0 otherwise. And something that I think it's interesting about this is that one of the advantage of having an energy function is that you don't have to convert that into a probability. So you don't need to calculate, you need to explore all possible combinations of values to calculate this normalization constant, right? Otherwise, if you have a potentially infinite set, you would never be able to do that, right? But in this case, they use the energy function because, well, we'll see later that it has some advantages, for example, for joint reasoning. But they convert that into a probability density using this normalization constant. And since we are only considering the x and y that are inside this finite set of valid combinations of parameters, then we can calculate this. So this is an overview of how the model works. Basically, you have a PSL program that is instantiated with a dataset, and then you have a symbolic inference calculating like which rule you have to apply. And when you choose that for calculating that, you will have some aid from a neural inference process. And then you have to assign values to those rules, which will also, sorry, you'll also have aid of this neural inference process. And then you'll have to calculate loss. And depending if you're doing learning or just doing an inference process, well, you'll update different things in here. But basically, the idea is that neural network predicts over a set of symbolic potentials that are created, sorry again, by a PCL program. And both the symbolic potentials and neural networks define a deep hinge loss Markov random field the way we have just seen. Remember that all PSL programs define a deep hinge loss Markov random field, but in this case, there is like a particular way of creating that field. So a little bit about inference and learning. Inference is the process of computing the output of the neural networks for each CNN, and then symbolic inference is minimizing the energy function over y. So in this case, you know the parameters of the potentials neural networks, and you also know the symbolic weights of the symbolic neural model, and you want to find the y again inside the set of feasible combination of variables that minimize the value, the energy function for that y. And the difference with learning is that in this case you have the WNN and the WPCL, and you want to find the y that minimizes this value. And when you learn, you want to find the WNN and WPCL that basically creates assigns the lowest energy to the correct values of the output and the higher energies to incorrect values. Learning is organized in learning objectives that map an energy function and a set of training samples with real value lost. And learning objectives are separable over the training samples as a sum of per sample loss functions. So you can apply, for example, batch gradient descents, or you can use just small sets of training example to do a gradual training. And again, the learning objectives is learning this. So here's what I was saying previously, that the loss function is basically the summation of the different loss functions applied to subsets of the dataset. Then you have latent variables. Stephanie is going to talk a little bit more about this, but you can have variables that are not directly extracted from data. And so because of this, all variables in the training settings are partitioned into vectors y, I, t, and c, y. Well, this basically, it means that you have some variables that are extracted directly from the data, while others are not. And you have a joint minimization process for finding the seeds and y's that give the lowest energy. And in the case of seed, you already have this y set on the function, while when you want to minimize the when you want to find the y that minimize the energy function, you don't consider the seed. And seed asterisk and y asterisk are the lowest energy states, given a particular sets of y, x, and x and n in the case of seed, and x and x and n in the case of y. A specific case of the learning process is constrained learning, and this is called when the per sample losses are not functions of seed asterisk and y asterisk, so they don't require any subproblem optimization. The idea is that constrained learning reduces the time required per iteration, but they are less expressive. Again, when Stefan is going to talk a little bit more about the differences when you use constrained learning or not. So here I have the idea of this slide is all interesting losses for a NeuPSL are a composition of the energy function. So they are derivatives of the energy function based on what you want to learn, which is WPSL, WNN, and GNN. I don't want to explain much about these formulas and the derivative process. You can watch them later with more time if you want. But the idea is that if you assume that the loss function is linear, then these formulas demonstrate that that you can calculate all derivatives straightforward. And then standard backpropagation based algorithms can be applied for both neural and symbolic parameter learning. The energy loss, I think Shamil already said it, but you can possibly use different energy loss functions to train models, obtaining different kind of results. But for simplicity, authors propose an energy loss function that minimizes the energy of the training samples, but doesn't require inference over all components of Y. So you don't have to have all components of Y to calculate the energy loss. And note that the parameters that minimize the loss function are the same parameters that minimize the summation of the bold capital phi per sample. So again, you can also take like partitions of the training set and learn the same. So per sample energy loss partial derivative with respect to WNN at shape position is this function over here, which is basically a derivative of the loss function based on WNN, which is basically the summation of these all of the derivatives of each loss potential symbolic potential loss based on WNN multiplied by each row of the symbolic parameters.